The last problem in this chapter is a Bernoulli's principle problem. So what's happening here, height is neglected because we're assuming that the blood in this problem is traveling horizontally. And so since it's traveling horizontally, height, which would be measured like this, can be neglected. And so the formula for Bernoulli's principle when height is neglected is going to be delta P. Delta means change in something. And so there's lots of deltas in lots of different situations. At this particular point, we care about the change in pressure inside of a blood aneurysm. So delta P equals 1/2, so just the number 1/2, times the density of whatever the fluid is that we're talking about, times V1 squared minus V2 squared. And those V's stand for velocity, so how fast it's traveling in the normal blood vessel and how fast it's traveling in the aneurysm. So obviously we're going to need to calculate a velocity here because the problem tells us that we have an area for the normal part of the blood vessel. So let's draw it out. Here is our blood vessel and there is the aneurysm. So this is the normal part. This is the aneurysm part. So the area in the normal part is going to be 1.0 meters squared. It tells us that it's traveling, so that is going to be the velocity of the normal blood vessel, 3.0 meters per second. And then it tells us that the diameter of the blood vessel increases by 20%, and then it's asking us to find delta P. And then it tells us the density to fill into this equation. So we can't use Bernoulli's principle to find a second velocity. We have to know the second velocity already. We know one of them, it's 3.0. We have to find a second one of them using some areas. So the formula that we're going to be using again is that continuity of flow formula. So A1 squared V1 equals A2 squared V2. So instead of it being big on the left and small on the right, the aneurysm is ballooning up after it's flowed through a normal blood vessel. So this is actually going to be the small side, and this is going to be the big side. So we have A1, we have V1, A2, and V2. So they told us the area of the normal or the small blood vessel is 1.0 meters squared, and it told us that it's traveling at a velocity of 3.0 meters per second. We're going to be looking for that second velocity to fill in here for the aneurysm. And we're going to have to figure out what the second area is. And we can do that pretty easily because they told us that the diameter increased by 20%. Now, in this situation, you don't have to go to the diameter and then increase it by 20% and then convert from the diameter to the area. It's okay if you take 20% of the area. So we're going to go ahead and say 1.0 times the decimal form of 20% is 0.2. And so 1 times anything is itself. So 1 times 0.2 is going to be 0.2. And so since an aneurysm means that it's getting bigger, it's ballooning up, we're going to add 0.2 to 1. And so the new area is going to be 1.2 meters squared. So A2 is 1.2 meters squared. So now we have everything we need to plug it into the continuity of flow equation. So we can go ahead and say that 1 squared is going to be 1. So A1 squared. Remember the velocity, we just bring it down, 3 meters per second equals 1.2 squared. So you can put it into your calculator like that. 1.2 squared is 1.44 meters squared times x, or V2. So to isolate V2 or x by itself, we have to divide by 1.44 meters squared to get it to cancel. Divide again by 1.44 meters squared. So in your calculator, 3 divided by 1.44 is going to equal a velocity of 2.08 meters per second. So we're now ready to put everything into the delta P equation. So delta P ultimately is what we're trying to calculate, equals 1/2 times the density of 1060 kilograms meters minus 3, and that is the correct units for this particular problem. You do not convert to grams per milliliter. Open parentheses, so your V1 squared and your V2 squared. Our V1 is going to be 3 because it's starting in the small vessel and traveling to the big vessel. But you have to square them, don't forget. So 3 squared is going to equal 9 meters per second minus this V2 squared that we just calculated. So 2.08 squared. That's going to be about 4.33. So 4.33 meters per second. So 9 minus 4.33 is about 4.67. And so we can multiply, we can cross that because we now have a velocity here, a single number. So 1/2 times 1060 times 4.67, that is going to equal 2.47 times 10 to the third pascals, because we are talking about the change in pressure. Again, this is another one of those that the textbook worked very differently than what I worked. I would not mark your problem wrong if you worked it how the textbook did, but this is how I prefer to work this problem. It makes a little bit more sense for me this way. So thanks, and let me know if you have any questions about example problem 7.